Yeah, okay, so it's my pleasure to welcome Yuka Hashimoto. He'll be talking about time series data analysis with reproducing kernel Hilbert C star modules.
Thank you for giving me a chance to talk about our current work. My name is Yuka Hashimoto. I'm a researcher at NTT Network Technology Laboratories in Japan. And today I'd like to talk about time series data analysis with reproducing kernel Hilbert system modules. Reproducing kernel Hilbert system modules are generalization of reproducing kernel Hilbert space, which is widely used for machine learning and data analysis. And this is a joint work with these people. And for more details, please refer to this archive paper. So in this talk, we begin by the motivation of this research, and then we explain the existing frameworks, reproducing kernel Hilbert space, RKHS, and vector-valued RKHS. Then we introduce the notion of reproducing kernel Hilbert system module. And then we apply it to analyzing interacting dynamical systems. And here we first explain existing methods in RKHS to analyze dynamical systems. Then we generalize it to RKHMs for interacting dynamical systems. So first we begin by a brief introduction of the motivation of our research. Reproducing kernel Hilbert space, RKHS, has been actively researched for data analysis. And in this framework, a sample X is transformed into a complex valued function through a map called feature map. And here we denote this feature map as phi tilde. And the space spanned by this complex valued function, phi tilde x, is called reproducing kernel Hilbert space. And although the original space is a finite, usually a finite dimensional space, RKHS are in general infinite dimensional spaces. So nonlinear relationships between samples in the original space is transformed into a linear one in an RKHS. And by using this property, we can analyze complicated dynamical systems in original space in RKHS. And also, we can apply it to classical methods like principal component analysis or support vector machine. And also we can apply it to learning complex valued functions because vectors in RKHS are complex valued functions. And there are at least two advantages of RKHS. First, RKHS has more representation power than the original space because RKHS are in general infinite dimensional space. And also we can compute inner products in RKHS exactly by computers. Although the although RKHS are infinite dimensional spaces. These two properties make RKHS widely accepted for data analysis. However, we think there is also disadvantage. And if we want to analyze multivariate data, because the inner product in RKHS are complex valued, information about interaction between the variables in data is degenerated by taking a complex valued inner product. For example, we consider these three two-dimensional vectors x1, x2, and x3. The first element of x1 and the first element of x2 are very close. But the first element of x1 and the first element of x3 are not so close. But the distance between vectors x1 and x2 and the distance between x1 and x3 are same. So if we calculate the inner product between x1 and x2 in RKHS, in an RKHS, and also if we compute the inner product between x1 and x3, these two values become same. So the information about similarities between pairs of elements of these vectors are degenerated by calculating inner products. So we consider generalizing algorithms in RKHS to RKHMs, reproducing kernel Hilbert modules for analyzing interaction of variables of multivariate data. So in the framework of RKHM, a sample X is transformed into a C-star algebra-valued function. We explain the precise definition of C-star algebra later, but here an important example of C-star algebras is the space of bounded and linear operators on a Hilbert space. And the module spanned by this C-star algebra valued function is called RKHM. This is a module which is a generalization of a vector space. And also we can consider a C-star algebra valued inner product in RKHM instead of the complex valued inner product in RKHS. And by using this C-star algebra valued inner product, we expect we can analyze interacting dynamical systems. For example, if a dynamical system has m dynamical elements, we can preserve the similarities between arbitrary pairs of elements in m by m in a m by m matrix. And in this case, if we set this C-star algebra as the space of m by m matrices, we can analyze the interactions between these elements in dynamical systems. And also, we expect we can generalize these methods in RKHS to RKHMs. There are two advantages of RKHM. First, RKHM is a natural generalization of RKHS. And also, as I explained, sister algebra valued inner products, like a matrix valued inner product, can describe information of interactions between variables. Let me summarize the objective of this research. In existing methods in RKHS, we transform samples into complex valued functions in RKHS. And then we can extract information of a relationship between these samples. On the other hand, in our methods in RKHMs, we transform this multivariate data into sister algebra valued functions in RKHMs. Then we can extract information of relationships between elements of pairs of elements. And in this talk, for complex valued objects, we use tilde like this. And for sister algebra valued object, we denote them without tilde. We now explain the definition of existing frameworks, RKHS and VVRK, vector valued RKHS. We begin by a positive definite kernel. A complex valued map is called a positive definite kernel if it satisfies these conditions. And by using this positive definite kernel, we can define an inner product. So these two properties corresponds to properties of inner products. The first property corresponds to the symmetricity of inner products, and the second one corresponds to the positive definiteness of inner products. And by using this positive definite kernel, let phi tilde x defined by fixing the second variable of k tilde. And the map phi tilde is called the feature map associated with a positive definite kernel k tilde. And we consider a space spanned by phi tilde x, like equation number 1. And in this space, we can define an inner product by using this positive definite kernel, like equation number 2. And here, an important fact is we can compute the inner product between vectors in this space exactly if we can compute the value of this k tilde. And the compression of this space by this inner product. It's called RKHS, and here we denote it by HK tilde. And although vectors in RKHS are complex valued functions, we often want to consider vector valued functions instead of complex valued functions. For this purpose, a generalization of RKHS called VV-RKHS is also proposed. In this framework, we consider an operator-valued positive definite kernel instead of the complex valued one. And the definition of the operator-valued positive definite kernel is like this, and this is very similar to the case of complex valued positive definite kernel. And here star means the adjoint of operators, and this inequality means this right-hand side operator is positive semi-definite. And by using this operator-valued kernel, we can define a map phi x by fixing the second variable of k, like the case of RKHS. Then we consider the space like equation number 3. And here we can define an inner product by this operator valued positive definite kernel and the inner product in this Hilbert space. This Hilbert space. And the compression of this space is called VV-RKHS, and we denote it by HKV here. So we now introduce reproducing kernel Hilbert C star module, a generalization of this generalization of RKHS and VV-RKHS. But before going into the definition of RKHM, we first explain the definition of Hilbert C star module. This is a generalization of a Hilbert space. And let A be a sister algebra. A sister algebra is a Banach space equipped with a product structure and an involution. And important examples of sister algebras are the space of bounded linear operators on a Hilbert space W and the space of L infinity functions on a measure space. In the case of A equals to the space of bounded linear operators, the product structure corresponds to the composition of operators, and the involution corresponds to the adjoint of operators. And let M be a right A module. And a right A module is a generalization of a vector space. And the scalar product in a vector space corresponds to the multiplication of an element C from C to a vector U from right. And in a right A module, we can define an A-valued inner product. This is a generalization of a complex valued inner product. And an A-valued inner product is defined like these equations and inequality. And these are very similar to the case of complex valued inner products. And the conjugate and the complex conjugate in the case of the complex valued inner product corresponds to adjoint in this case. And also this inequality means this inner product is a positive element in A. And here positive means, for example, in the case of A equals to this, the space of bounded linear operators, a positive corresponds to the positive semi-definiteness of operators. And by using this A-valued inner product, we can define an A-valued absolute value and a standard real valued norm like this. And if A equals to the space of complex values, these two notions coincide. But in general, A-valued absolute value has more complicated structure because it takes its value in A. But it contains more information than a real valued norm. And if an A module, if an A module is equipped with an A-valued inner product and complete, it is called a Hilbert C star module. This is a generalization of a Hilbert space. And for data analysis, we want to solve a minimization program. And so for this purpose, we introduce the notion of orthonormal. Vector Q is said to be normalized if the inner product between Q and Q itself is idempotent. And this is, I think this is not so obvious extension in the case, extension of the case of Hilbert spaces. But it will be useful for data analysis actually. And we will explain how we can use this property in data analysis later. And the definition of orthogonal is same as the case of the Hilbert spaces. And then we can show minimization property. And let V be the module spanned by an orthonormal system, and let P be the projection operator. And then the projected operator on this module, this submodule, minimizes the difference between the original vectors in V. And this property is very fundamental property in Hilbert spaces. And often used for solving minimization programs. And this important property is also available in Hilbert system modules. And we now explain the definition of Hilbert system module. Reproducing kernel Hilbert system modules. We consider the same type of positive definite kernel as the case of vector-valued RKHS. And define a feature map phi like this. And then consider a module spanned by phi x. And here an important difference between RKHM and VV-RKHS is this coefficient takes its value in A. This coefficient contains in A. In the case of VV-RKHS, this is a vector in a Hilbert space W, this W. And also, the inner product in VV-RKHS is a complex valued one. But in the case of RKHM, we can define an A-valued inner product like equation number 7. And like the case of RKHS, the compression of this module is called reproducing kernel Hilbert system module. And in this talk, we denote it by MK. Let me summarize the difference among RKHS, VV-RKHS, and RKHM. An RKHS is associated with a complex valued positive definite kernel and composed of complex valued functions. And inner products in RKHS are complex valued. A VV-RKHS is associated with an A-valued positive definite kernel and composed of vector-valued functions. But it is still a Hilbert space, and the inner product in VV-RKHS is complex valued. An RKHM is associated with an A-valued positive definite kernel and composed of A-valued functions, and also it is a Hilbert system module, not always Hilbert space. It is equipped with an A-valued inner product. In fact, RKHM is more general than RKHS and VV-RKHS. If we set A as the space of complex values and set K as K tilde, this RKHS and RKHM coincides. And also, if we set A as the space of bounded linear operators, then this VV-RKHS is equivalent to the tensor product between this RKHM and this Hilbert space W. So the existing algorithms in RKHS and VV-RKHS can be reconstructed by using the framework of RKHM. And also we expect we can extract more information by using RKHM, then by using RKHS and VVRKHS.
So I had a question here. So why did you say that we should expect to extract more information?
Because RKHM is more general, and in fact, this is a larger space, larger set than RKHS and VVRKHS.
Yeah, okay. I'm just trying to see. I mean, if the space is larger, I'm not sure why we should expect. Yeah, yeah. Just continue. You can talk later. Yeah.
Okay, I will explain the examples. Yes, and we now consider applying RKHM to analyzing dynamical systems, but before considering RKHMs, we first review the existing methods in RKHS for analyzing dynamical systems. We consider dynamical system like equation number 8. And here T denotes time and F is in general a nonlinear map. And we consider a Perron-Frobenius operator in an RKHS. This is a linear operator defined like equation number 9. And this Perron-Frobenius operator describes the time evolution of this dynamical system. And an important fact is the nonlinear relationship between xt and xt plus 1 in the original space is transformed into a linear one between phi tilde xt and phi tilde xt plus 1 in an RKHS. So we can use standard tools of linear algebra to estimate the Perron-Frobenius operator only with given observed data. And so we can estimate the behavior of dynamical systems only with given observed data by using Perron-Frobenius operator. And also, because a Perron-Frobenius operator is linear, we can apply the eigenvalue decomposition, also called modal decomposition, for example, to capture a behavior of a dynamical system. So, for example, if this Perron-Frobenius operator only have discrete spectrums, we can decompose it like equation number 10. And here the only term depending on time t is this eigenvalue lambda. So by computing this eigenvalue, we can understand a behavior of dynamical system along time. And let me summarize the framework of the analysis of dynamical systems in RKHS. We are only given finite observed data, and then we transform this data into vectors in RKHS. Then we estimate the Perron-Frobenius operator in RKHS. We now consider generalizing it to RKHM. We consider a dynamical system like equation 11. Here, the ith element of xt plus 1 is described by the first up to the mth element of xt. And here, Fi is in general a nonlinear map. And we can define a Perron-Frobenius operator in an RKHM like similar to the case of RKHS. But here an important difference is this is a sister algebra valued function instead of a complex valued function in RKHS. So it has more information than a complex valued function. And then in like the case of RKHS, the nonlinear relationship between xt and xt plus 1 is transformed into a linear relationship in RKHM. And the linear operator describing this linear relationship in RKHM is called a Perron-Frobenius operator. And to describe interactions between elements in a dynamical system, we consider a matrix valued positive definite kernel. Here, let K tilde be a complex valued standard positive definite kernel. And then we set a matrix valued positive definite kernel like equation number 13. Here, the ij element of kx1, x2 describes the similarities between the ith element of x1 and the jth element of x2. So this positive definite kernel, this matrix valued positive definite kernel describes similarities between arbitrary pairs of elements in vectors x1 and x2. By using this positive definite kernel, we consider estimating the positive Perron-Frobenius operators. And in practical situations, we are only given finite observations, and we want to understand the original dynamical systems by using these finite observations. And for this purpose, we consider the minimization program like equation 14. And here we consider minimizing the difference between these two vectors because the Perron-Frobenius operator describes the time evolution of the dynamical system. And here, k hat is a linear operator on this finite dimensional module. And to solve this minimization program, we construct orthogonal projection operator because of this minimization property. So we consider generalizing Gram-Schmidt orthonormalization in Hilbert space to Hilbert C star modules to construct this projection operator. So we first explain normalization. And in our case, the positive definite kernel is a matrix valued one. So we consider the case A equals to the space of matrices. And let Q hat be a vector we want to normalize. And then there exists a matrix P hat, which can be multiplied by right to Q hat, and Q hat P hat is normalized. And to construct this P hat, we compute the eigenvalue decomposition of the inner product between Q hat and Q hat itself. Please recall the definition of normalized in Hilbert C star module. The Q and the inner product between Q and Q itself is idempotent. And so we compute this inner product. And after computing the eigenvalue decomposition, we keep eigenvalues which are larger than epsilon squared. We fix a positive value epsilon and keep eigenvalues which are larger than epsilon squared. And we throw away eigenvalues smaller than epsilon squared. And then we can construct B hat. And actually, epsilon is arbitrary. And it describes the amount of information to be reduced by normalization. And for example, for noisy data or the case of the large number of observations, we set epsilon as larger value. And then we can keep only principal informations of this noisy data or large number of observations. And next, we consider orthogonalization. And orthogonalization is very similar. It's the same as the case of Hilbert spaces. And then we can construct an orthonormal system of this Hilbert C star module. And then we can construct an orthogonal projection operator by using this orthonormal system. And then we can compute the solution of this minimization program to estimate the Perron-Frobenius operator, like this. And also, this matrix is a matrix representation of the estimated Perron-Frobenius operator. And next, we consider, and by using this estimated operator, we next consider the modal decomposition. We first define eigenvalues and eigenvectors in Hilbert C star modules. And eigenvalues and eigenvectors are characterized by this equation, like the case of Hilbert spaces. But here, A is a matrix, and A is a matrix valued eigenvalue. And precisely, we have to consider a quotient set, because if A is a matrix valued eigenvalue, the C inverse AC for an invertible matrix C is also an eigenvalue of this linear operator. But in practical situation, in the case of our estimated Perron-Frobenius operator, it is easy to compute these eigenvalues and eigenvectors. And we want to compute eigenvalues and eigenvectors of this estimated Perron-Frobenius operator. In fact, it is a matrix valued matrix, but it can be regarded as a large complex valued matrix. So we can compute eigenvalues and eigenvectors of this matrix, and then we can construct eigenvalues and eigenvectors of this estimated Perron-Frobenius operators. So by using this eigenvalue decomposition, we can consider decomposing information of similarities between pairs of elements of dynamical systems. By the definition of the Perron-Frobenius operator, because it describes the time evolution of the dynamical system, the vector corresponds to the observation at time S can be written like this. And we replace this Perron-Frobenius operator by the estimated Perron-Frobenius operator. And then we apply the eigenvalue decomposition and obtain the decomposition like equation number 17. Here, please recall this matrix represents similarities between arbitrary pairs of elements in dynamical systems. The ij element of this matrix is the similarity between the ith element and jth element of xs. So this is the decomposition regarding the similarities between pairs of elements in dynamical systems. And here, the only term depending on time s is this eigenvalues. So if we extract the terms corresponding to eigenvalues whose absolute value is 1, we can extract time invariant information about similarities between pairs of elements. We briefly show numerical results. We consider two time series data about indoor and outdoor temperatures, and we consider this type of delay coordinate. And here, YT represents the indoor temperature, and ZT represents the outdoor temperature. And because this delay coordinate is 20-dimensional vector, we set this value m to 20. And then we computed the time invariant term in this decomposition. The result is shown in figure 2. And here, the magnitude of the element corresponding to the similarity between ZT and YT plus 4 is large, these yellow ones. And actually, by this original data, we can see the indoor temperature becomes high about 4 times step later than the outdoor temperature becomes high. So we can extract the time invariant relation between these indoor and outdoor temperatures by using this decomposition. And finally, we explain our ongoing work. We consider extending the discrete setting to the continuous setting. So far, we have considered the finite elements in dynamical systems. And there are finite elements in dynamical systems. But instead of this, we consider there is a function, and there is a continuous function, and they varies it, and it changes by time. And we consider the extension for theoretical analysis, and also for the case where the number of elements m is unknown or not fixed. And for this continuous setting, we consider the equation like equation number 19. And here xt is a function instead of a finite dimensional vector. And then we can generalize this setting to the case of this continuous case. And in the case of discrete, and for discrete case, A is set to be the space of matrices. But for continuous case, we consider setting A as the bounded linear operator. And also we can generalize this matrix valued positive definite kernel to operator valued one. And so for considering this extension, we believe RKHM is effective tools, powerful tools for analyzing this kind of dynamical system. In fact, there is a possible method with VVRKHS to achieving this goal. For example, if we set W to M-dimensional space or W to L2 function space, then we can approximate the Perron-Frobenius operators on this subspace of VVRKHS. But please recall the vectors in VVRKHS are vector-valued functions. And this phi x is an operator-valued function. So for obtaining vectors in VVRKHS, we have to choose a vector in this Hilbert space to construct vectors in VVRKHS. So we don't know how to choose these vectors efficiently, especially in the case of W is infinite dimensional case, in the case of this continuous case. On the other hand, by using RKHMs, we can simply construct the submodule spanned by these observations, and then we also normalize these vectors. Then we can estimate the Perron-Frobenius operator. In this case, the notion of Hilbert system modules provides us the effective design of algorithms. And in conclusion, we have applied RKHMs to time series data analysis. And because inner products in RKHMs are C-star algebra valued, these inner products can capture more information than complex valued ones, and it enables us to extract information about similarities between arbitrary pairs of elements. So that's all we have to say. Thank you.
All right, thank you very much.
Thank you.
Thank you. Any questions? Yeah, Peter, you can go ahead.
So
yeah, we can hear you. Yeah.
Pardon?
No, now we can hear you. Yeah.
Okay, so thank you very much for your talk. Very well paced, very nice. Actually, I have a comment and a question. So allow me to start with comment on nomenclature. I suppose the operator you have used is by most of the authors called the Koopman operator and not the Perron-Frobenius one, if I wasn't quite mistaken.
Yes,
the composition of an observable with the dynamics.
Yes, but this is defined on This is defined on RKHS. And
yes.
So actually, this corresponds to a Dirac measure centered at X. And then this is a push forward. This corresponds to push forward measure of the Dirac measure And so this is a Perron-Frobenius operator.
Okay, so apparently there is an interpretation going on I didn't get. Okay, so you know what you are doing there. But I do have a question as well to this slide, if you allow. This D is a domain which is, I suppose, there to represent a set such that your Perron-Frobenius operator is mapping elements of D back into your RKHS, right?
Yes.
Do you have any idea how this this curly D, this calligraphic D, looks like? So do you have some kind of characterization of D, or can you tell me something about this set? Does it even exist?
Yes. Actually, this D, we don't know if we can choose D as this whole space, but if we can, if we choose a proper RKHS, these phi x are linearly independent. So then in this case, we can choose D as this space, this pre-Hilbert space. And so by choosing, and in the case of these vectors are linearly independent, this Perron-Frobenius operator is well defined. But
how do you know that if you hit one of those elements with your Perron-Frobenius operator, it is still going to be an element of the reproducing kernel Hilbert space? That's what I'm wondering about.
So by this definition, this the vectors in the form of this phi tilde x, the finite sum of this phi tilde x can be in this HK tilde. But so for the vectors in this space, if we compute k tilde v for v in this space, k tilde v is also in this space in RKHS. But we don't know if we can extend k tilde to whole space HK tilde. And the Perron-Frobenius operator can be unbounded.
In the RKHS norm?
Yes.
That's what you mean, okay.
Yes.
Okay, thank you.
Thank you.
All right, any other questions? Yeah, okay, thank you very much. Let's thank the speaker for the nice talk. Thank you very much.
Thank you very much.
Thank you.